So, good morning everyone, and hope everyone's fine this morning. So this morning we're going to be talking about dependent sources, and dependent sources are very important. So far you've only come across independent sources, but most of the work you'll be doing forward to this is going to involve dependent sources in some shape or form. Right, so a dependent source is one that depends on something else. And so far we've only met independent sources. And an independent source could be something like a battery, whose voltage is just fixed by the value of the battery, it's not affected by anything else. Or a power supply where you've set 5 volts on the power supply and that's what comes out. So that's an independent source. Its output is independent of anything. A dependent one, by comparison, has an output value that depends on some other feature, some other input. And notably transistors and op-amps, transistors we're going to be doing next week, op-amps we'll do shortly afterwards, they contain dependent sources, so we have to understand dependent sources before we can analyze these types of circuit usefully. And as we said, they are dependent on the value of something else in the circuit, so they are variable, which obviously helps to make the analysis a little bit more complicated. So in terms of dependent sources, there are 4 possibilities that we can consider. So what we've got is an arbitrary network in the middle, so a connection of all kinds of things in here, but fundamentally they're 2-port networks. Okay, there's a port here and a port here, 2 ports, and one is an input normally, and in this case we're inputting a voltage, and in this case we've got an output, and the output is also a voltage. Okay, and the only things that we've really got to consider are voltage and current. They are the only 2 variables that we're going to consider going forward for these type of systems, for our analysis purposes anyway. So in this case we're putting in a voltage and we're getting out a voltage which is A times bigger than the input voltage, and therefore the output of this system depends on the value of the input. If V1 is small, this output will be smallish, and if V1 is big, then this output will be huge, assuming that A is a positive number, bigger than 1. So that's voltage in, voltage out, and the link between the two is called the gain. Or the amplification, and it's usually called A. The other ones to consider is if we have an input voltage coming in and we end up with an output current, and the current here is defined by GM. So V1 is the input voltage, it's multiplied by some factor GM, some number, and that gives us a current. And this is called, this has dimensions of conductance and is defined as G. Which is 1 over R, and M comes from the term mutual, so it's a mutual conductance of this network. So there is some method to the naming of this. Likewise, we could have a current coming in through the arbitrary network, and that results in another current coming out, which is A times bigger than the input current. So that's just a current gain, and that's a dimensionless quality, as is this gain here. Gain is dimensionless when the units are the same on both sides. In the case of a current coming in and a voltage coming out, we have a constant of proportionality which has units of resistance. So effectively we're just implementing Ohm's law into this relationship here. So controlling current coming in gives us a bigger current coming out. I'll say bigger, it depends on the value of R, of course. So these are the definitions of that, and that's what we end up with in our 4 possible combinations. So that leads us on to nodal analysis with a dependent source. So it's just 5 amps, it's fixed. This one is an independent source, a dependent source, because the value of this current source depends on the value of I1. If I1 varies through here, for whatever reason, this current source here will also vary. So that adds a bit of complexity into the analysis. So we have to allow for this by introducing a constraint equation. And we introduce a constraint equation, and then we can basically follow the same rules as we did before. So the solution is similar to before, so I'm not going to labour the point of here. You should get the general idea now that we're doing a nodal analysis. So we just add up all the equations for node B, node C, so I've labelled the nodes in this case, and you can see that we end up with this dependent source appearing in the node C equation, which you'd expect because it's just a source that's coming into node C. And there's four elements in this equation. So we've got 0.3 VC, which is coming from here, 0.2 VC minus VB, which is coming from this one here. We've got 5 being the current source, and minus 4i being this current source. And again, if you're unsure about the signs, draw your arrows on here for your definitions and work it through there. You're just applying the same rules over and over again. And then because we've got too many variables in here, not enough equations, we will have to have this constraint equation. So we introduce a constraint equation which is that I1, which is our unknown, is actually defined by 0.2 times the voltage across here. So this is just defining Ohm's law effectively for this resistor here. So now we have another equation we've introduced that just says that I1 is actually defined by this. So we can start to make substitutions if we want to, and solve it in the normal sort of way. So it says here, make the substitution for I1. So take I1, this bit here, plug that into there. This one way of doing it. Collect the terms together. You can make a matrix if we're seeing maybe familiar matrices now, and so we would know at least that once we've got it into this matrix form, that it's solvable. But because of this source that we've introduced now, it's not a symmetric matrix anymore, so we can't just look at it from that viewpoint. And then if you want to go and solve this for some practice, this is what I got. I got VB equals 5 and VC equals 0 in this case. So if we want to do a mesh analysis of the dependent source, we can follow exactly the same kind of rules. Here is a voltage source dependent on the value of V1. Here, this one, so 5 V1. So we don't know what V1 is at the moment. V1 is defined by whatever currents are flowing through here, and that's driven by this voltage source over here. And it's it's a mesh current, so there's two of them to worry about. So again, we can introduce the constraint equation, and then just solve it by normal mesh analysis. So just solve for the mesh. So we've got all the sources around here. So we've got this one, 18 I1. We've got an I1 minus I2 multiplied by 2 down here, and 110 being the source. Set that equal to 0. Mesh 2, we've got the opposite of this one because the current's going the other way. We've got 5 V1, which is our dependent source, and we've got 16 I2 coming from here. And again, we've got too many variables, not enough equations, so we have to get some more information from this, and we can see that V1, the dependence of this, it depends on the voltage across here. So we just need to calculate what this voltage is here, and that will be 2 I1 minus I2. So now we've got enough equations with enough to solve for the unknowns we've got. Substitute for V1, collect all the terms together, make the matrix equation. We've got that. We can solve that as normal. So if you want some practice at solving these things, you can go away and solve that and verify that I1 equals I2, which equals 6.111 amps in this case. Right, so the third type of analysis that we've done nodal, we've done mesh, and we did superposition. Can we apply superposition to dependent sources? And this turns out to be a bit of a grey area. Most texts will say never suppress a dependent source, and in fact the previous lecturer who used to teach Dan and Neil's course used to teach this. He would say never to suppress a dependent source, and this has been taught for years and years and years, and it's not necessarily true. And in fact, Professor Damper, who's now retired, who did do that, had a big argument with me about whether you could or couldn't do it. I said you could, he said you couldn't, and that inspired him to write this paper can dependent sources be suppressed in electrical circuit theory? And he proved that they could. So I was right, as it turns out. And the reason I was right was because I did what you lot are not doing. I bunked off a lecture at my undergraduate level when they taught me this. So there was a lecture going on about never suppress a dependent current source. Yeah. So I missed that. So I've been quite happily suppressing dependent current sources and teaching it for years, until someone actually stood up at the back of the class when we were live and said, "You've suppressed a dependent current source." And I said, "Yes." And he said, "You can't do that." And I said, "I've just done it." And we went through various arguments. I went to see Bob because he taught them all that they couldn't do this, and so he ended up writing this paper. Long story short, and he got all the credit for it, but he couldn't get it published for a long time because all the people who review these things, everything is peer reviewed, which means it gets read by other so-called experts in the area to make sure it's not rubbish. And they said, "This is not true. It's rubbish. You can't publish this. Everyone knows you can't suppress a dependent source." And even though he proved it, he went through about 3 different reviews before anyone actually allowed him to publish it. So you've just got to be careful about these things. Question everything, I suppose, is the answer. But it is the safest approach, and you don't really need to do it. But let's see what you can do. This is a circuit with a dependent source on it. This is the dependent source. It's a current source, and it's related to IB, which is its input current. And that comes from this source voltage here driving a current through the rest of the circuit. This is actually a representation of a transistor circuit, which we'll be doing when we do transistors. And we can look at this using superposition just to show how careful we need to be. So the normal approach will be to suppress everything and then unsuppress sources one at a time and then add up the results. So we would unsuppress VS first, maybe then VCC, and then the current source BFIB, and then add the results up. And if we do this here, we can get the wrong answer in several different ways depending on how we interpret it. If we're not careful, get the right answer if we are careful. So let's suppress VS and the current source, and unsuppress VCC. So we've suppressed VS, and that gives us a short circuit because it's a voltage source. And we suppress the current source, and this gives us an open circuit. So this is the sort of circuit we're looking at now. It's a little bit odd, we've got a wire floating on its own. The output voltage we're looking at over this resistor and the power supply here. It's an open circuit in this loop, so therefore no current flows, therefore this voltage here must be the same as this voltage here, no voltage drop across here. So V out is equal to VCC in this case. Okay, that's nothing contentious about that. Okay, so if we suppress VCC and replace it with a short circuit, and we keep the current source suppressed, so that's an open circuit, and then we look at what happens with VSS, or VS rather. Okay, so there's a current flowing around here, but there's nothing going on over here, and there's no voltage source over here, so V out is going to be 0, V out being the voltage at this point here. So nothing else to be said about that either, really. And then the interesting part, if we suppress VS and VCC, so again VS has a short circuit, VCC has a short circuit, and we've got our current source in here, we end up with an interesting solution then, because if we look at this, we can recast this circuit with these things suppressed as this, because definition of IB is 0, and therefore this is 0. So if this is 0, it's effectively suppressed anyway, so we end up with this. So we could view that as being that V out is equal to 0. We could also view it as actually, well, let's not define this as being 0 here, we'll just keep this open as BFIB whatever, and we'll ignore the fact that IB is defined as 0 because there's no source in this part of the circuit where IB comes from, so IB can't be anything except 0 in this case. But we'll keep an open mind on that, and we'll keep it like that. If we do that, then we can say that V out is equal to BFIB RL, because that's the current circulating in here, and we've completely ignored the fact that IB is defined as 0 at the moment, so we ignore that. So that would give us, if we then remember to relate IB to whatever VS was in the first place, it would have been VS RL over RS. Okay, so there's a confusion. We've got two possible answers here. One slightly complicated and abstract, and one more direct, just says it's 0. So if we add all those up, then we can have a choice of two answers. We can have this answer if we choose to have not defined IB as 0, or we could have had Vout equals VCC minus 0, which is just VCC. So the first one is actually the right answer, as we should see when we do transistors. But depending on how you define things, this is could be taken to be the answer as well. But if we just look at the circuit overall, we could say, well, there's very little chance that the output will be VCC under all conditions for the rest of this circuit. So that should give us a clue that maybe there's something mistake going on there. So another interpretation of how to solve this that I've seen, which you might come across, but I start by telling you it's not correct. So I'm just explaining the method and why it's not correct. Okay, so that's just for interest's sake, really, because it can happen. This is the circuit we're looking at. It's the equivalent, effectively, of two separate fragments of circuits if we maintain the connection of ground or reference to be the same potential across here. So this is this one here and this is here. So they're the same, it's just we've taken this wire away, but because it's referenced to the same point, that makes no difference. So we've got two separate fragments of circuit, which is, on a complicated circuit diagram, is easy. This could be, a drawing or a source over here somewhere, and this could be an output down here somewhere. And although they're linked, it's not obvious they're linked because they're not in proximity to each other. So this is where the confusion starts to come in. So it's possible that you could analyse it as two different circuits. So we've got this circuit here, which has two sources, this current source and this voltage source, and then there's this circuit here that has this voltage source over here, but it's not actually part of this circuit, we might think, and it might not be obvious from our circuit diagram, so we might choose to leave that on the side. So eventually we might actually term this as being a sort of a linearity problem, where we're saying it's a function of this one and then plus the function of these two superimposed. But let's just look at what happens if we keep them separate at the moment. So what we would say is, okay, well, we're not really aware about this part of the circuit, so we'll ignore it for the time being, but we've got this circuit over here. So we'll suppress the current source, for example, because there's two sources, replace it with open circuit, and then we can see that with this source left in, the output voltage measured at this point would just be VCC, because there's no current flowing, same as before. Then we would suppress VCC, open up the current source, so VCC is replaced with a short circuit, open up the current source, and we would see then that Vout is equal to minus BF IB RL, which is BF IB is the value of the current source, and it drives through RL, which will give us the voltage when this is suppressed. And so we add those two answers together, and that gives us VCC minus BF BSRL over RS from that. And then we might get a bit confused, and then we might later say, actually, there's this other part of the circuit as well, we need to consider that. That's only got one source in it. We'll just suppress that and see what happens. And if we suppress that, then the current going through it will be 0. And we look at the output, we know that IB equals 0, so that Vout is equal to VCC, because we notice that they're linked at that point. So then we add that result in, because we think we have to, and we end up with Vout equals 2 VCC minus 6. So it's added on to the previous two subparts of the superposition we do. And if we don't notice that IB equals 0 and follow the logic, we end up with Vout equals 2 VCs minus 2 of these things. They're both wrong. It's the wrong approach, because we can't really separate these circuits out because they are intrinsically linked through this source. But of course it's not immediately obvious they are linked either, because this current source here is dependent on IB, and we might not know that IB is independent because there is no source over here labelled IB. There's only a source labelled VS, and VS actually is indirectly giving us IB through this resistor. So it is linked to this source over here, but it's sort of hidden in the definition. And if this is, as I said, if this is over here in the circuit diagram and this is over here in the circuit diagram, you can end up with a bit of confusion. So it just leads to confusion, really. So, as a general rule then, we have to identify all linked sources carefully. So in the diagram below, we can see with some care that this current source here is linked and dependent on this voltage source over here. Although this one is defined by IB, which is the current down here, IB actually is being defined by the value V here and this resistor here. So this source is driving the current IB through here, which is then changing over here. So it might not be immediately apparent what's linked to what, particularly if these things are separated, as we've discussed. But identify them, and then we would treat linked sources as the same source. So we would say this is one big virtual source, these two combined together. We treat them as one, and then we only suppress these linked sources together. So we don't suppress this one on its own and then this one on its own. We suppress both of these at the same time, and we open them both up at the same time. And by making that change, we then follow the normal instructions, and we will end up with the right answer. And for the purposes of clarification, this is the right answer: VCC minus BFPS RLRS, where we've substituted BS over RS for IB here, because that's the definition of it. And then you need to just check any answers with common sense. Right, so circuit theory, other approaches. So there are two little tricks that we need to be aware of that are quite useful going forward, which allow us to apply this network theory that we've done so far. And if the circuit is in a certain form, such as a ladder network or a star delta transform, then we can apply a few little shortcuts to it and get the answer a bit quicker. So, ladder networks. So this is a ladder network, so called because it looks a bit like a ladder. If you turned it on its side, you could potentially try and climb up the rungs. So it's just a big collection of meshes. Alternatively, it's a big collection of nodes. So we can start to look at this and go, oh, we can solve this by mesh or nodal analysis if we want to. We can work out what the currents are in here by applying all kinds of mesh, but it's going to get a bit complicated. And there's a certain amount of symmetry here. Maybe we can exploit that. And the fact that there's a single driving source, so we've just got one source coming in, which is a pretty common sort of situation to be in. It's a signal in, and then we have a signal out over here, and there's some processing in the middle. This means that we can try and simplify the solution a little bit, a bit of a shortcut. So if we want to find out V0 for a given input, so here's 10 volts coming in, and we want to know what's the output coming out over here. We can use this method. We can calculate the total resistance and the resulting source current. So we can turn this into one big resistor and then just apply Ohm's law. Okay, that sounds like an ambition, but we can do that. How do we do that? So we can start to look at this and we can start to apply the rules. So this is our network as it stands. And what we can do is we can say, well, look, if we just want to analyze this, we won't worry about this bit at the moment. We can say that we can add this resistor and this resistor together to make a 3 ohm resistor. And so that this resistor can be absorbed into this one, and then we can redraw the circuit like this. So all we've done is we've taken these two resistors and we've turned them into this 3 ohm resistor. So as far as analysis of this circuit is concerned, these two are the same. Yeah, we haven't added any other components, we haven't taken any components away, we've just absorbed it into here. Now, note, the original output terminals are gone, and this means that V0 is now effectively 2/3 of the way up this resistor. So we've lost V0. But that's okay, we'll get that back later, because what we've done is we've simplified this circuit a little bit. Okay. We can carry on doing this, we can collapse this further, because this now is two resistors in parallel. And we can turn that into one equivalent resistance, which is 1 over 2 plus 1 over 3, and then we take 1 over that, and that gives us the equivalent resistance here, and that comes to be 1.2 ohms. Okay, so now we've taken that and we've turned it into that, and now our circuit is looking a lot more simple. You know, we've collapsed this part of the circuit into an equivalence, and now you can see that we can do it again. We can add that one to that one, and that will give us an equivalent resistor, and then we can add that one. We end up with parallel ones as well. So we carry on doing this, and eventually our circuit turns into this, and this we will recognize as a potential divider. Okay, so the values are starting to get a bit complicated, but the circuit itself is very similar. And from this we can see that the total current, would it matter which way we add the resistors? I'm not sure I understand the question. You just have to follow the rules for serial resistors and parallel resistors to get the equivalent. So unless you can ask the question a bit clearer, I don't quite know what your question means there. Sorry. Right, so we can work out which order. I'm still not clear. Like parallel first or series and parallel. Well, I think as Mr. Omar said, I don't think it particularly matters. You just got to abide the rules. You have to do it in the right order. All right, you've got to. Let's go back. Okay, you can't add that one and that one, for example, because there's this one in the way, and you can't parallel that one and that one because this one's in the way. All you can do is do it sequentially coming from this end. So you've got to take that and that, add it, because you can see they're a series one, and when you've turned that into a series one, then you're left with a parallel one, and you have to add that. So you've got to do it in the right order. Okay, so those add up to become that. Then you can see that you've got two parallel ones. You can't do anything with these because they're a bit complicated. Yeah, they become parallel, and then you end up with a new series one, and you can add those in series. That's the way to do it. So hopefully that answers the query. Right, so you end up with the current. So you can work out the total current through here because only one current now. This will be expanded out and the current will split, but we know fundamentally that the current is going to be 10 over 3.048, so it's 10 volts over the total resistance, which is 2 plus 1.048, which is 3. Okay, so that's straightforward enough. And the current divider rules then gives these currents shown. So we then say, we know what this current is in here now because we've got this potential divider. Let's expand our circuit back again initially. So we go back to this stage, and we can see now that that current, which is still flowing through here, our 3.281 amps, now has to split into two, and we can apply the current divider rule that we learned about probably in the first lecture to work out the split of the currents down here. And we can work that through, and we can work out we get 1.719 and 1.562 amps in this part of the circuit. And then you can probably see where we go from here. We start to expand this resistor back out into its form. So that's what we would start to do. So we expand that back out again, and we know that this current is still flowing, and it's now got a divide between the two. And you keep expanding it like that until if finally at the end you get back to your original circuit, and we now know that we've got 0.625 amps going down here, and we've got 2 ohm resistor, so the output voltage is 1.25 volts. You could have done it by mesh analysis, but it starts to get complicated. Here we're just applying it in small chunks by collapsing and expanding the circuit, and it allows us to get to an answer without too much stress. So there's another method which I find is a slightly more complicated, but other people might find that they appreciate it. So we assign a symbol to the last branch current, and then work backwards through the network to find an expression for the source voltage in terms of this current, and hence network currents and voltages are shown. Find V0. So it's the same problem again, 10 volt source, we want this output voltage. An alternative technique, label the branch currents. So we've got I5, I4, I3, this one is also I5, remember, I1, I2. So we've labelled all those. We've noted these voltages here, V0, V2, V1. And then we can say that V2, this one here, is equal to 3 times I5. So I5 goes down here, and we know it's a 3 ohm resistor because it's 1 plus 2. Okay, and that gives us the voltage at this point here. Then we can work out that I4 is equal to V2 over 2, and that equals, because V2 equals 3I5, we can say that's 3I5 over 2. And then you can go back through, you can apply Kirchhoff's, so we're effectively applying a nodal analysis, Kirchhoff's current law, and then make a substitution for I5. So you can say I3 is equal to I4 plus I5. I3 is I4 and I plus I5, and we know what I4 is from here, and that allows us to start to get things in terms of just I5. Work out the voltage by applying Ohm's law across V1, and then just keep working that through, and eventually you end up with a simple Ohm's law equation that says what the voltage is linked to the current in I5, and that tells you what's going on. So I5 becomes 40 over 64.625 amps as before, and V0 equals 1.25 volts, same as before. So what we're really doing is just applying sort of Kirchhoff's laws on the fly as we go along, because they're very simple little meshes, so we're just almost doing mesh analysis in our heads. There's other ways of looking at this. We can think of the ladder network as a cascade driven by an ideal source or one with a source resistance. So this is where you start to apply a bit of imagination and try and squash these circuits into a form that you've seen before, that you know how to analyze. So we can take our ladder network and we can break it into repeating sections until we run out of components, and this is just a practical voltage source. So an ideal voltage source in series with resistance. So this is a standard source plugged into our circuit, which is a repeating set of elements. Each section can be represented in a variety of essentially equivalent ways. We could plug a whole load of these things together to make our ladder. We could plug a whole load of these things together to make our ladder. Or we could say it's this type of connection, and this is what's called a star connection, because it's all coming to a point in the middle. And this is what's called a pi connection or a delta connection, because if you join these together at the bottom, it makes an upside down, well, it makes a delta. But we can replicate that circuit we've just looked at by either using these sections or any one of these sections and just replicating them. So if we know how to analyze for all these different sections, then we can just multiply that out. So often these sections will be identical, there'll be n of them, and such ladder networks can have some interesting properties, which allows us to maybe simplify what's going on. So this is the same as we had before, but this time we've split the source resistance into two, because it was a 2 ohm resistor before. So we've just said, well, that's the equivalent of 2 1 ohm resistors in series, and now you can see we've got a source, an ideal source here, and then we've got 3 bits of sort of upside down L-shaped ladder, would be one way of viewing it. You could say it's also a star connected to a delta. You can see that you've got backwards L here if you absorb that back into the source again. So there's lots of ways of viewing this as a section. So what we've done here is, as I said, we've split this source in, and we're going to be looking at it in these backward L's, upside down L's. Right, let's see, what's that? It looks like a cascade of voltage dividers. That's one way of viewing it. I suspect that if you view it that way, you might not find it easy to get to the answer, but let's just have a look at what we've got here. So, and this is where Thevenin becomes quite useful, because if we look at the first section, we've got this source, which we've defined as being a practical source because we've given it a source resistance, and then we've got this 1 and 2 ohm L-shaped network plugged onto it. And we would say that is the equivalent in terms of Thevenin-ness. We can say this is a 2-port network. Let's have a look at what we can do. This is the equivalent to a 5 volt resistance and a 1 ohm resistor, And you can sort of get that by saying, okay, we want the Thevenin equivalent of this. Let's take the open circuit voltage of this. And so we look at, say, what's the open circuit voltage of this? It's driven by 10 volts. It is a potential divider. 1 plus 1 is 2, so that gives us 2 ohms in the top part of the divider. We've got 2 ohms in the bottom part of the divider. That's an equal divider, so we can just say that this is going to be half this supply voltage here as an open circuit. If we put a meter on here and measured the open circuit voltage with no current flowing, we would see 5 volts. And then if we want to work out what the resistance is, we would suppress this, and that goes short circuit, and we see what we've got left. We've got a 1 ohm resistor in series with another 1 ohm resistor, which makes a 2 ohm resistor, and that's in parallel with this 2 ohm resistor. And a 2 ohm resistor in parallel with another 2 ohm resistor gives us a 1 ohm resistor. So the Thevenin resistance is 1 ohm, the open circuit voltage or Thevenin voltage is 5 volts, and so this circuit here can be simplified to this. Okay, and that brings it back to a source again, and then we can plug that onto the remaining part of our network, and we can do exactly the same thing again. So we can deduce that the output resistance is constant, independent of value of n, number of sections, and the output voltage is V over 2 to the n, where n is the number of sections. So we had 3 sections in our little network. So for n equals 3, we get V out equals 10 over 8, which is exactly this 1.25 volts, which is exactly as from methods 1 and 2. Okay, so a little bit of homework there is to go back and expand this out through the various sections and just check that you're happy with that. But it's quite neat. So if you can recognize something as this type of circuit, and you can simplify it down, or you can massage it into a shape that looks like this by dividing resistors up, you can maybe put it into a form that's relatively easy to solve. And this is used quite a lot, and this is, we actually analyse this in a bit more detail in the 3rd year, if you do my course in the 3rd year. And it's exactly the principle that's used in this thing called an R2R digital to analog converter. So this is effectively what's inside a digital to analog converter. So a digital signal comes in here, so it's, this is a digital input, and this little network here converts that into a voltage, which is then amplified by this amplifier, and you get a voltage out here which is related to the value of the digital number that's been put in here. And the value of these resistances is defined, and you can see we put a ladder network here, and you can analyze this ladder network and work out exactly why these values are as they are, and what the voltages and currents are, and what the significance of all these switch voltages are then. So this is a 4-bit converter, and a 4-bit converter means there are 16 possible combinations of digital input, so this is a 16 level system. The nice thing about this is that all these resistor values are the same. Which you'll find out as you go forward with these sort of digital systems, that the more bits you have, with other techniques you have to be very accurate in the relationship between resistors, and quite often some of these will go down in value, but if you use this ladder type network approach, they can stay all the same kind of size, and you just keep adding sections to it, and you can have as many bits as you like then. So it does have a practical analysis, so some simple analysis of ladder networks. Simple application of Thevenin to a network leads to, if you invented this, a great deal of profit, because people like to buy D to A converters, and this is a good structure, so you'd have been ahead of the game. So the last thing we need to do is something called a star delta transform, which again is just an application of some simple rules. We can show that this type of network, which we call a star, is equivalent to this type of network if there's a certain relationship between the value of these resistances. So we have to define these as being combinations of these, and then it's an equivalence. So note that node Q is eliminated. Yeah, Q. We haven't got no Q here. We've got rid of a node, but we've created a mesh. Sometimes called a Y to delta, or a T to pi transformation. You can see why it's called a T, and you can see why it's called a pi. And sometimes it's a star. If you bend these points up a bit, you end up with a star or a Y. And if you connect these 2 points here together, you end up with a triangle. Okay, so it's It's not very imaginative really. So equivalence requires that the resistance between all pairs of terminals must be the same. So if you looked into here, this terminal between P and T, you would see a certain value of resistance. And for these to be equivalent, you'd have to look into this terminal here and P and T here. You'd have to see the same value of resistance. So whatever you see looking into here as a current, you need to see exactly the same thing in here in terms of the equivalence. And that's really our starting point. So for terminals P and S, because we got three sets of terminals to worry about. We've got P looking into P and T. We've got looking into S and T, and then we've got looking in to P and S. So there's three ways of looking at this. So let's just start with terminals P and S. So if we connect a circuit to P and S and see what's going on in that little loop there, we would say that the resistance between P and S is equal to R1 plus R2. This one's not connected, so there's nothing going on in this bit. So the circuit is just this, there's nothing going on in here. So RPS is R1 plus R2. And in the delta network, if we did the same thing and connected between P and S and said what's the resistance looking in through here, then you can see that any current coming into here can either go through RA and out through S, or it can come in, go through RB, around here, up through RC and then out of S. So we've got a current divider going on in here. So we've got RA, and these two stripes here mean in parallel with. So that's RA in parallel with RB plus RC, because RB and RC are in series as far as the current is concerned. Current comes into P, goes around here, goes into RB, comes in here, goes into RC and then out. Okay, and some of it will go through RA. So we've got RA in parallel with RB plus RC, and you can apply standard manipulation of resistors there to get RA RB plus RA plus RC over RA plus RB plus RC is the equivalent resistance looking into these two terminals. So it's starting to get a bit complicated, but it's just simple rules being applied. So hence these have to be equivalent to each other. So R1 plus R2 must equal RA RB plus RA RC over RA plus RB plus RC. And RA plus RB plus RC tends to appear a lot in these equations and takes a lot of effort to write it down, so we would just call that R delta. So this is just a shorthand that says that's the equivalent of all the resistances added up. It just makes it easier to write. Okay, so we've got R1 plus R2 equals RA RB RA RC over the total resistance RA plus RB plus RC. And we do the same thing for terminals P and T. So if we look at P and T here, we're going to see R1 plus R3, and this one doesn't appear because this is open circuit, so there's nothing going on here. So you've got R1 and R3. So any current coming into here, the only place it can go is down here and out, because this is where the only connections are. These are left open at the moment. Likewise, RPT, you start to see a pattern here. If we connect between P and T, we say if a current comes in here, where can it go? It can go through RB and out, or it can go through RA and then through RC and then out. So we've got RB in parallel with RA and RC, and we end up with RA RB plus RB RC equals delta R delta. So we've now got another equation, and we do the same thing for terminals S and T. So we've got RST equals R23, and you get the general idea now. ST, the current can go through here, and then it has to go through these two as well. So these two are in series, but they're also in parallel with this one, and that gives us the third equation. So we can now form a new equation from 1 plus 2 minus 3. So what we're really trying to do is just separate out one of these variables from the equations that we've got. We've got enough equations to worry about it. We could probably solve it by matrices if we wanted to. But if you simplify this down, it's straightforward enough. We get R1 is equal to RA RB over R pi, R delta. Remember, R delta is just RA plus RB plus RC. So that's starting to define the equivalence of what R1 would be if only we knew what these were. And if you do it again, same kind of analysis, you can separate out R2 and R3, and we end up with very similar relationships. So if we know what the value of R1, R2 and R3 is, then we can calculate the values of RA, RB. Likewise, if we know what RA, RB and RC is, we can then work out the equivalent for R1 and R2 and R3. So that allows us to swap between them. Similarly, and I don't propose to go through this is something that you can do in your own time. It's just manipulation of those equations to get the RC and RB as subjects to the equation. And this allows us to then extract the values of the resistance that we're interested in. But what we're trying to get to is that RA, for example, is equal to, so this resistance here is equal to this expression. So if we know what R1, R2 and R3 is in our circuit, so this is our physical circuit, but we want to analyze it in this form, the value of RA becomes this expression, and we know R1, R2 and R3. And likewise, a shorthand for this that is quite common is to say that this is the cross multiplication of all possible values of the resistance, R1, R2, R1, R3 and R2, R3. We just write that as a shorthand as R star, because it just takes a lot to write that bit down, and that's where mistakes happen. So you just define that as R star as a shorthand, and there we go. So we're starting to see now that we've got a very similar relationship in both directions for this circuit. Now the reasons why this is important is because if any of you end up doing power engineering, this is very, very popular in three-phase circuits, and so electricity is supplied in as AC, but it's generated in three phases that are equally spaced in phase from each other, and there's a lot of balancing goes on. So you'll be going forward, if you do power engineering of any description, you'll be very, very familiar with star networks and pi networks, because this is all to do with mains electricity generation, and you'll be able to switch between these two representations really, really quickly. But this is the fundamentals of how you actually get there. So that's quite nice. So we've got to the end of the circuit analysis part of the course, which means that next week we can move on to looking at transistors and how to actually build amplifiers and start to apply some of this nodal mesh and superposition work to help us actually analyze useful circuits and design things that can do things that we want. So at that point I stop and say thank you very much, and I hope that was interesting. Go back through the notes, try out some of the examples, just expand them out, make up your own examples and try them, and you can always put them into the simulator to check if you really want to. So there's lots of opportunities for trying stuff out. Okay, so I'll see you next week.